A narrow, high-temperature plume just fired from 3I Atlas, and it's pointed almost exactly at the sun. That's the image, a focused beam of gas and dust, not a diffuse fan. It looks like a nozzle opened on the comet and blasted inward. That single sightline changes how we read everything else. Here's what's irrefutable from the picture and immediate follow-ups. The plume is collimated, it's hotter than the ambient coma, and it appears suddenly, hours, not weeks. Those three facts force a short list of physical explanations. The simplest, cleanest one is a pressurized vent, exposed at a single location. In vacuum, pressure escaping through a long, narrow fissure will collimate. Add a rotation axis that keeps the vent facing the sun during the active window, and you get a sunward jet, pure and maintained for hours. Why does that matter? Because normal comet outgassing is broadly diffuse. Sunlight sublimates surface ices, gas fans away, and radiation pressure reshapes the tail. A narrow, sustained beam requires geometry and pressure. It implies sealed volatile pockets or layered ice structures that preserved material until a breach. For an interstellar body that's plausible, its thermal history is unknown, so it can carry supervolatile reservoirs that react violently on first solar exposure. Three immediate consequences are worth highlighting. One, the visible brightness spike isn't just reflective area increasing, it's active mass injection, fresh micron-sized grains that scatter light extremely well. Two, the Jet-S thermal signature implies energetic release beyond gentle sublimation, either large volatile flux or a mechanical breach releasing stored energy. Three, that thrust is directional. Every eruption nudges the nucleus, changing spin and stressing the structure. One powerful vent can start a chain reaction toward breakup. If you want a tight narrative for a VO line, a confined vent, open solar heating triggered explosive outflow, and a focused beam shot at the sun, a geometry-driven pressure-fed event that may tear the comet apart over weeks. Hawk, that sentence contains the observation, the mechanism, and the stakes. Keep watching the nucleus for cracks. This jet isn't just dramatic imagery, it's a ticking mechanical process. Part 2. Instruments, inconsistencies, and the tests that matter. Now the image is the headline. The instruments give the footnotes that force new models. Spectra taken around the eruption show a simultaneous spike in volatile lines, CO2 and CN, and a centrally concentrated metal signature. Nickel shows up stronger than typical comet baselines. Photometry records a rapid brightening, roughly a magnitude or so over a short window, and dust production estimates put the erupted mass in the millions of kilograms range for that event. Those are big specific numbers, lots of material released fast. Now the puzzle? Astrometry and orbit fits. When teams plug in non-gravitational terms to account for jet thrust, the measured orbital push is smaller than you'd expect from that much mass loss. In plain terms, 3I Atlas is shedding a lot of stuff, but the rocket effect on its path is weaker than simple momentum accounting predicts. That mismatch narrows plausible explanations. Either the nucleus is much more massive than our size estimates imply, or a portion of the observed energy isn't converting into balanced recoil, for example, forward-biased ejecta, or energy emitted as high-energy photons. That's where reasoning pays off. If ejecta is strongly forward-directed, more material thrown ahead than expelled symmetrically, the recoil on the nucleus is smaller. If energy is emitted as photons, X gamma, rather than bulk momentum, again the expected thrust is lower. Both are testable. Spatially resolved IFU maps will show ejecta geometry. High-energy monitors will reveal unexpected photons. The chemistry also points us. Metal-rich grains explain rapid brightening without huge recoil because they boost visible scattering while adding less net push per unit brightness. So, what to do next? And fast. High-cadence photometry to catch further spikes. Simultaneous optical IR spectroscopy to watch CO2, CN, and metal lines evolve. IFU mapping to trace where species are emitted spatially, and precise nightly astrometry to flag sudden acceleration changes. If we see continued brightening without matching orbital response, the anomaly becomes robust, and the competing physical models will either survive or collapse under coordinated multi-wavelength scrutiny. There's a simple way to think about this: geometry plus pressure. A comet's surface isn't a uniform skin, it's cracked, pitted, layered. If sunlight breaches a crust over a volatile pocket, pressure builds in vacuum. That pressure doesn't diffuse the way it would in an atmosphere. Instead, it finds the weakest path and blasts out. If that path is a narrow canyon or a tubular vent, the flow collimates. You get a jet. Now add rotation. If the vent faces the sun during the active window, it will erupt sunward. If the nucleus spins slowly, or the vent sits in a deep, shadowed fissure that opens only occasionally, that eruption can be short and focused. A beam rather than a fan that explains directionality and why the jet held its alignment for hours instead of sliding from side to side. Energy source matters. Standard comet jets are driven by sublimation. Sunlight heats ice and it turns to gas. But the intensity we measured from 3I Atlas requires either a huge volatile reservoir or an extra push. Possibilities aren't mystical. Internal pressurization via trapped supervolatile ices, CO, CO2, N2, exothermic chemical reactions in organics, or even fracturing that exposes deeper, hotter layers. For an interstellar object, any of those are more plausible because its thermal past is unknown. It may carry ices preserved at extremely low temperatures that react violently on first solar exposure. Finally, plasma and magnetic interactions can shape the outflow. The sun's magnetic fields and the passing CME can channel charged dust and ionized gas, effectively sculpting the jet's visible shape. Think of the sun not only as a trigger, but as a shaping force. Its fields can pinch and guide the plume, making it appear narrower and more stable than a purely neutral flow would. That coupling of mechanical venting and electromagnetic shaping is why the plume looked both focused and unusually hot. In short, breach a pressurized, volatile pocket, vent through a narrow geometry, time the opening to rotation and solar impacts, and let solar magnetic structure focus the output. That combination produces a sunward beam that looks impossible. Until you lay the physics out, spectra don't lie. They tell you what's in the gas and dust and how it's released. For 3I Atlas, we saw three marks that force new thinking: extremely high CO2 ratios, strong CN bands, and a concentrated nickel signal near the jet base. Each on its own is interesting. Together, they become a puzzle. High CO2 implies supervolatile rich material that is why the object reacts strongly at larger distances than most comets. These ices vaporize with less heating. CN indicates organic-bearing ices and fragmentation of complex molecules. But the nickel is the real eyebrow raiser. Metal lines, so centrally concentrated, means metal-bearing grains are being liberated from very near the nucleus, not just background dust. That suggests either metal-rich surface layers or localized vents blasting through metal-bearing strata. What could produce that? Several natural options: a parent body formed in a metal-rich protoplanetary disk, impact gardening that concentrated metals near the surface, or thermal fractionation that left metal grains behind as volatiles sublimated. For an interstellar body, earlier collisions and different formation chemistry are plausible, so the nickel signal may simply reflect a different birthplace. The combined chemistry also explains the jet's visible behavior. Metal-bearing micron grains are highly efficient scatterers. When they're injected in large numbers, visible brightness spikes dramatically. If nickel-rich grains vaporize under extreme heating, they might also produce short-lived metallic vapor that shows up as concentrated lines that would generate a high visible flux without producing proportional bulk recoil, helping explain the brightness-thrust mismatch observationally. The next steps are clear. Follow the CN-CO2 ratio As the jet evolves, watch the nickel line's spatial profile and check for transient metal species in UV and X-ray bands. If metals drop out quickly while volatiles persist, it suggests a surface-limited metal layer. If metals persist or increase, we're looking at a deeper heterogeneous interior. Either way, the chemistry tells the formation story. And 3I Atlas's formation looks unlike typical comets. Every eruption nudges the nucleus. The jet exerts torque and linear thrust. Small in isolation, but repeated or intense enough, those pushes change spin rate and stress. For 3I Atlas, the measured non-gravitational terms show asymmetry consistent with a dominant vent. That vent's torque could spin the object up, increasing centrifugal stress until fractures propagate. There are two live scenarios. Scenario A: vents release pressure, and the body relaxes. The spin rate stabilizes. The comet survives, perhaps shedding layers but remaining one object observationally. The light curve flattens and jets become less intense. Scenario B: venting accelerates spin or opens new fractures, cascading into fragmentation that shows up as sudden multiple nucleus condensations in high-res images and rapid drops in nucleus-centered brightness, as mass disperses into fragments and dust. Timing is crucial. If vents remain active through perihelion and the object experiences repeated solar impacts, the chance of breakup climbs fast. Early fracture lines seen in imaging are warning signs, micro cracks that can become macroscopic splits under torque. Also, asymmetric mass loss alters orbit subtly. If the center of mass shifts during fragmentation, trajectories will change and prediction becomes harder. What to watch next? High-cadence imaging to catch secondary fragments, polarimetry to detect rapidly changing grain populations, and updated astrometry nightly to trace any sudden acceleration shifts. Practically prepare for a possible fragmentation window in the coming weeks. And if that happens, the scientific payoff skyrockets. Fragmentation exposes interior material directly. It's the best way to sample primordial composition. If 3I Atlas breaks, we will learn far more in days than months of steady activity ever could. We don't guess now, we test. If you want to turn curiosity into answers, here's the playbook astronomers are already using, and what I'd follow if I had the feeds open right now. First, high-cadence photometry. Get fast, repeated brightness measurements every night, ideally multiple times per night, from survey telescopes and backyard arrays. The light curve slope is the simplest discriminator: steady decline, plateau, repeated spikes, or chaotic jumps. Each maps to a physical scenario: steady outgassing, exhaustion of a vent, recurrent venting, or fragmentation. Short cadence photometry also catches minute scale bursts that point to micro-explosive events. Second, simultaneous spectroscopy across bands. Optical spectroscopy tracks CN, C2, and metal lines. Near IR captures CO, CO2, H2O bands. UV X-ray gamma picks up any high-energy photons that ordinary sublimation can't explain. Schedule coordinated windows where optical, IR, and high-energy monitors run together during predicted solar impact times. If you see a gamma to X-ray spike aligned with an optical surge, that's a smoking gun for an extra energy process. Third, integral field spectroscopy, IFU, and spatial profiling IFUs show where species are concentrated spatially. Metals near the nucleus, CN extended. That radial info tells you whether things are surface layer limited or coming from deeper vents. Map species at multiple position angles to check for rotating jets and localized vents. Fourth, precision astrometry. Nightly track non-gravitational accelerations closely. If mass loss increases but orbital residuals don't scale, you've got an energy mismatch that needs explaining. EG, forward biased ejecta, photon-dominated energy, or exotic physics. Fifth, polarimetry and grain size monitoring. Polarization tells you grain size and structure. A sudden shift to low polarization signals small, fresh micron grains. High polarization points to larger, fluffy aggregates that helps interpret brightness jumps as dust-dominated versus gas-dominated. Finally, prepare for fragmentation. High-resolution imaging, HST, adaptive optics, nightly can catch small secondaries forming. If fragments appear, switch to rapid cadence and spectroscopy of each piece. Fragments are direct windows into interior composition. Do this in coordinated windows tied to solar activity forecasts. Solar flares and CMEs are the triggers. Plan gamma, X-ray, and particle monitors to run concurrently. Run Bayesian hypothesis tests nightly. Which model, pressurized vent, impact exposure, exotic annihilation, best fits the multi-wavelength data? Keep the priorities tight. Time is the limiting resource, not ideas. We can boil the possibilities down to a short testable list, ranked by plausibility, given current data, pressurized vent, exposure of supervolatiles, most plausible. A sealed volatile pocket, CO2N2, breaches and vents through a narrow geometry, explains focused beam, rapid mass loss, CO2 dominance, and strong CN from organics, predicts repeated vents until the pocket empties and a predictable decline in activity. Testable, declining bursts, CN-CO2 ratios fall over weeks. Structural fracture revealing deep layers, plausible. A thermal crack exposes previously buried layers with different chemistry and metal inclusions. Explains sudden nickel-rich grains plus intense dust. Predicts a one-time large release followed by a plateau. May lead to fragmentation. Testable, single big spike. Then fragment detection, solar-triggered electromagnetic shaping, paired with one or two. Solar magnetic fields and CMEs shape an otherwise diffuse outflow into a narrow beam, making it appear far more collimated. Explains narrowness and stability during solar events. Testable. Beam alignment correlates with local IMF, interplanetary magnetic field direction. Modeling should reproduce beam morphology, impact-triggered venting, low to medium plausibility. A micrometeorite hit exposes a volatile pocket, causing a jet. That explains one-off eruptions but is less likely to produce multi-day stable jets unless followed by additional hits. Testable, sudden spectral spike, without precursor solar activity. Exotic physics, partial antimatter domains, speculative but testable. If tiny anti-domains exist and annihilate on contact with incoming matter, you'd see high-energy photons, gamma, X-ray, that don't match sublimation spectra, plus forward-biased energy release. It is low prior probability, but the data mismatch, brightness versus thrust, odd metals, makes it a hypothesis that can be ignored. Testable, coincident high-energy detections during solar impact windows. Energy budget inconsistencies resolvable by annihilation energy. Each theory makes clear, observational predictions. The next few weeks of targeted, multi-wavelength observations will collapse the model space quickly. The key is not which idea is sexiest, it's which one survives simultaneous photometry, spectroscopy, astrometry, polarimetry, and high-energy monitoring. This isn't just another comet clip for your feed, it's a live experiment on interstellar material, and the payoff is enormous. If the jet is explained by pressurized supervolatiles, we learn about volatile retention in cold interstellar bodies and about how planetesimals transport and preserve ices across galactic distances. That changes models of planet formation and volatile delivery to young planets. If metal-rich grains dominate, we learn about protoplanetary disk diversity, how some systems produce metal-concentrated planetesimals that informs everything from core formation to dust processing in disks. If solar magnetic shaping is confirmed, we gain a new understanding of star small-body plasma interactions, how magnetic fields sculpt ejecta, and how charged dust behaves under real stellar conditions. If the exotic hypothesis, annihilation, antimatter survives tests, the implications are seismic. We'd have a natural laboratory for physics beyond standard comet chemistry. It would force reconsideration of formation scenarios and survival mechanisms for antidomains in space, and require follow-up theory and observation at the highest energies